Okay, so today I'd like to look at another problem from Morin. This is problem 3.52. And the question is, we're looking at a projectile on level ground, no drag, the usual assumptions, launched with speed v0 and angle theta. And we want to determine what angle theta, or what minimum angle theta, should we launch this projectile at, such that the distance from the launch point to the projectile is always increasing, or at least never decreasing. Now, why this question would even make sense in the first place, if you think about it, if I launched a projectile, say, straight up, it would first get further away, and then it would come back. So we would eventually have it return to us. The distance would decrease at some point. As I decrease that launch angle, it'll move away from us, but we want to make sure that we launch it at an angle such that it's always moving away from us, no matter whether it's moving up or down. The distance to us should always be increasing. And the question then is, what is the maximal angle at which we could launch that? We know that straight up will give us, it will eventually return. What's the largest angle that we could have it constantly moving away? Recall that we have our usual constant acceleration kinematics equations for both the position and the velocity. We'll take use of both of those. Okay, well, the first thing we should probably do is calculate this distance. So let's go ahead and do that. Notice we'll just use the Pythagorean theorem here. We have our various equations for the x and y coordinates as a function of time. Okay, if we plug those both in here, we have no problem. If we expand this out, notice that some things can simplify using the Pythagorean trig identity. And now we can go ahead and try to set this derivative, or the derivative of the distance, equal to 0. The reason for that is this distance we want to be always increasing. So what we're really trying to do is say that the rate of change of this value is positive, or at least non-negative. Now, that's going to be a little ugly with this square root here. We'd probably rather not have that. And so when we maximize d, or when we set the derivative equal to 0, we could also just use the fact that any function will have a max or min in its derivative, or I should say its derivative will be equal to 0 whenever the function squared's derivative is equal to 0. We can do a quick proof of that. Notice that if we take this derivative using the chain rule, if the derivative of the function itself is equal to 0, then the derivative of the function squared will also equal 0. It doesn't guarantee that a max is always a maximum and a min is always a minimum, but an extremum of d will always be an extremum of d squared. So let's just get rid of the square root here, and we'll take a derivative of d squared. Okay, so taking the derivative of this with respect to time is pretty straightforward. We do want to set this equal to 0, or rather, we want this to be greater than 0. If we go ahead and factor out a t from every term, and actually let's factor out a g squared also, we'll end up with something that is a t times a quadratic polynomial in t. Okay, so looking at this inequality, we see that either the term on the outside will be equal to 0 to find the places where this inequality might be saturated. Well, we do already know that t is greater than 0 by our choice of coordinates and origin here. Time is going to start at 0 when we launch the projectile. G is obviously a positive number. So we're really mostly interested in where is this quadratic greater than 0? Now, there are a couple ways of going about this. We could go ahead and pull out the quadratic formula. Let's go ahead and do that at the top of the next board. Okay, in general, we'll be able to find the roots of this polynomial, in other words, where it's equal to 0, using the quadratic formula. Now, in this case, what I'm really interested in is not just setting this equal to 0 and finding the roots, but the whole point is we never want there to be any roots. In other words, if we are expecting our projectile to always be increasing its distance, then this should never equal 0. I want this parabola, or this t squared with a positive coefficient term, to not have any real roots, because if there was a real root, that would mean that there was a time, some time, at which the distance, or distance squared, is, at least momentarily, not increasing or possibly even decreasing. So this ultimately boils down to us not wanting there to be any real solutions to this inequality. As such, well, the b term here and the a term, which in this case is just 1, those are real. We have no issue. It really all boils down to looking at the discriminant of this polynomial. If I can arrange for the inside of this radical to be negative, that will guarantee that this quadratic is always positive. We can even think about this graphically. I'll call this. So if I call this whole thing, say, y of t, we want there to be no times at which this value is equal to or negative, equal to 0 or negative. That ultimately means we should only have complex roots for this, which ultimately means that the discriminant should be negative. So let's see what that is in our case. Well, the b value is this bit in front of the t. Our a value is just the number 1, and our c value is this constant term. And this gives us an inequality that we want to solve for theta. Notice that when I square this out, v naught squared over g squared and v naught squared over g squared are both just positive constants that will end up canceling out. Distributing the square, this becomes an 8. Gives us a nice equation to solve for theta. Notice also that since we want this to be negative, we are going to end up getting a maximal value for theta. If we go ahead and plug in this value to our calculator, we can find that this condition in which the distance is always increasing from the launch point will hold for any theta that's less than about 70.5 degrees. Any angle that we launch our projectile from that is less than this value will always have the projectile increasing its distance as it moves away. But if I launch it at a greater than 70.5 degree angle, we'll end up with some point somewhere on the trajectory where the distance gets longer and then somehow gets shorter. Something that we don't want to satisfy this condition. So that is our maximal angle, QED.